Good morning or good afternoon. It's Miss Bauer here, and today we're going to talk about inverses. Now, what you need to know, or the NTK for inverses, is that an inverse relation exists if and only if one relation that contains the point AB, whenever the other relation contains the point BA. So if one function had 3, 5, then the other one would have to contain 5, 3. Now, the inverse of a function f of x is expressed with this notation, and that's f to the negative 1 of x. Or sometimes you'll just see f to the negative 1. Now, we don't read it like f to the negative 1. We read it as f inverse. Or you could say the inverse of f of x. Now, the graph of the inverse should reflect over the line y equals x. And that's because our x and our y are going to flip, so it should reflect or flip over the line y equals x, which you might recognize as your linear parent function. Because our x and our y's are going to flip, your domain of your original function is now going to become the range of your inverse function. And you could probably guess that the range of your function is going to become the domain of your inverse function. Okay? And like we talked about compositions the other way, a quick way to check if two functions, f and g, are inverse functions is if f of g of x equals x and g of f of x should also equal x. And that's using compositions. There are other ways to check if you have inverse functions, but we'll get more to that later. We'll get more into that later. Now, a function f of x has an inverse function if and only if each horizontal line intersects the graph of f of x and at most one point. Okay, this is called the horizontal line test. Now, you checked if something was a function using the vertical line test, so then you use the horizontal line test to see if the inverse function is there. So, the horizontal line test is just the inverse of the vertical line test. And you'll typically see HLT for horizontal line test and VLT for vertical line test. Now, a one-to-one function will pass both the vertical line test and the horizontal line test, and that's because no x value is matched with more than one y value and no y value is matched with more than one x value. And we'll do an example of that here in just a moment. Just know that if f of x is one-to-one, then your inverse is a function, meaning that your inverse exists. But if f of x is not one-to-one, okay, maybe every input has one output, but every output has more than one input, then that means that your inverse is not a function, and therefore your inverse does not exist. Now, you might be going through and reading all of this vocabulary and you're thinking, Miss Bauer, I don't even know what this means. And that's okay, because we're about to get into some examples where we're going to go over this and it's going to start to make some sense. So if I have this table and it says find the inverse R of each relation S and then determine whether the inverse is a function. So what I currently have right now is S. What I want to find is r. Now, what we said earlier was that for every function, the inverse has the opposite. So if my original function has negative 2, 6, let's label this x and y, then that means our inverse function should have 6, negative 2. And if our original function has negative 1, 5, then our inverse function should have 5, negative 1. And if our original function has 0, 4, then the inverse should have 4, 0. The inverse would have 3, 1, and the inverse would have 2, 2. Now, if I go back and I check this and I ask you the question, is this a function? You check, does every input have one output? And it does. Now over here for our inverse, I'm going to go ahead and check, does every input have an output? And if you check, it does, which means that both of them are functions. Meaning that this is called 1-to-1. So let's take out another one. Now I have a set of points and I'm going to go ahead and check. Is this currently a function? So negative 2, 7, 0, negative 3, 2, 1, 4, 5, 5, 7. For every input there is one and only one output. So this is a function. Now I'm going to figure out what r is, my inverse, and I'm going to go ahead and flip all of these coordinates. So negative 2, negative 7, my x and my y, it's going to become negative 7, comma negative 2. My next point would be negative 3, 0. And then my next point would be 1, 2. The next point would be 5, 4. And the last point in this relation would be 7, 5. Now, is that a function? Does every input have one and only one output? And if you check it, yes, it does. So both are functions. Meaning this is 1-to-1. So hopefully you're seeing now that if every input has one output and if every output has one input, then both of them should be functions, meaning they're 1-to-1 and our inverse will exist. Okay, now how do we check that on a graph? Well, this says graph the inverse on the graph below. So let's start out with just picking some points and kind of going from there. So if I take f of x and I make a table of points, I'm going to use these 3 points right here. So this point right here would be negative 1, 0. My next point would be 0, 1. And then my next point would be 1, 2. My inverse is going to flip all of those points. So I'm not going to have negative 1, 0 anymore. Now I'm going to have 0, negative 1. I'm going to have 1, 0, and I'm going to have 2, 1. So if I go put those points on my graph, so 0, negative 1 here, 1, 0 goes here, and 2, 1 goes here. Keeping in mind that it's not going to be a straight line. It's not going to do that. It's going to curve how this curved. So now it's going to kind of curve this way. So if I'm graphing this, I can also think back that because my x and my y flipped, remember that it should reflect over your linear parent function. So remember that graphs will reflect over your linear parent function, which was just f of x equals x. So on a graph, essentially, it will go from corner to corner. So what you can do is just like that. I can sketch that in there, and then now I have a much better idea of kind of where this graph twist and turn. So as you'll see, it will kind of go up here. It will come down here, and then it's gonna cross there like that. And your graph doesn't have to be perfect. Now, if I asked you if this was 1 to 1, if I asked you if the inverse even existed, that's when you can use the vertical line test and the horizontal line test to check. Now, vertical line test, VLT and HLT, is not an accurate justification. You can't say the inverse exists because of VLT and HLT. What that does is that helps you check if the function is 1 to 1 on a graph. So what that means is that it passed the vertical line test, but because our inverse is going to reflect, before I reflect it, I can just check the horizontal line test, and that gives me a heads up before I reflect it. So let's keep that in mind as we go on to the next one. Now, I have a function here, and it says if it exists, graph the inverse to f of x on the graph shown below. And if it doesn't exist, then I need to explain why. Now, as I go through here, and let's just go ahead and pick some points. So what I have here is f of x. So I'm going to use these points right here. So I'm going to use those points. So this first one is -3, 0. That next one is -2, +4. Then I have the origin, 0, 0. And then I also have 1, 4. Now, f of x is a function. If I go through and list all of these out, every input is going to have one and only one output. This would pass the vertical line test. So keep that in mind. F of x is a function. But if I were going to take those points for my inverse, now I have 0, -3, 4, -2, 0, 0, and then I have 4, 1. You'll notice that the inverse is not a function. And you could look on your graph and see it's not going to pass the horizontal line test because all of these values here are going to hit here, and you're going to have multiple outputs for each input. So the inverse is not a function. So what that means here is that it's not 1 to 1 because only f of x was a function, not the inverse, which means that the inverse does not exist. Which means that you don't have to graph it. Now, how do I know what points to pick on my table? Part of that was just from experience, but what you can do is you can check the horizontal line test, and if you caught it, what broke the horizontal line test was those points right there. So that's part of how I knew to pick those points, okay? Remember that some part of it could be a function, but the other part could not be a function. Therefore, it's not 1 to 1. 1 to 1 means that both f of x and the inverse are functions. And if it's not 1 to 1, then the inverse technically doesn't exist. So let's take a look at a couple more. Graph the following functions, determine if the inverse exists, and if it does, let's graph it on the same graph below. If it doesn't exist, then let's explain why. So taking a look at this one, if you remember, this is slope-intercept form, or y equals mx plus b. So our slope is going to be -0.5, which is really just -0.5. And our y-intercept would be -3. So I'm going to start by graphing that here. And -0.5 means I'm going to go down 1/2. And notice that I'm giving myself quite a few points on this. Now, we've talked before about how the majority of lines are functions, okay? Now, I'm going to pick a couple points on here just to prove a point. If my original function, f of x, has the points, and I'm going to pick the intercept. So I'm going to pick these two intercepts. has -6, 0, and 0, -3, then my inverse intercepts should flip, meaning that now I have 0, -6, and -3, 0. And now I'm going to go plot those points on my graph. Remember that on a graph, f of x and the inverse should be reflections over your linear parent function. So you can kind of use this to guide you. What's over here should flip over here, and then what's over here should flip over here. So if my intercepts are at 0, -6, and -3, 0, if you remember from geometry, all you need is 2 points really to make a line. I can clearly see here that both of these are functions. So it's existing. I'm going to leave it on my graph, and I could say that this is 1-to-1 if I wanted to. Now, let's take a look over here at our quadratic. I know that it's a quadratic because of x squared. I also can think back to my quadratic parent function and my parent function transformations. If this is a quadratic, that's going to be a parabola. Remember that this -2 should shift it right to, so I'm going to say it translates right to. And up 1. So I'm going to take my parabola, I'm going to take that u, and now it's going to go right to up 1. And then from there, we've talked about how you go over 1, up 1, over 2, up 4. And then I'm going to make that U shape. Now, h of x, this function, this quadratic, is a function. Every input has one output. But the question is the inverse a function? And this is where you have to think. There's multiple values that I can plug in for x where I would end up with the same y, because I could plug in negatives and positives and I would still kind of end up with the same answer because of squared. And another way to check that is if it's horizontal and I'm seeing all of these right here breaking my horizontal line test. So the inverse is not a function. Now, what I don't want you to say is fails horizontal line test. Now, that's a quick way to check it. It doesn't pass the horizontal line test, so it's not a function. But I don't want you to say that. You can say the inverse is not a function. You could say something like every output had more than one input, or just keep what you know about functions and say every input has more than one output, or just say input has multiple outputs. Keep in mind that horizontal line test is just your way of checking it. What that's telling you, though, is that it's not one-to-one. Therefore, the inverse, and to put h, the inverse does not exist. So the main thing to remember for graphs is that you can always pick points and make a table. If it is an inverse, it should pass the horizontal line test, okay? So that's a way to check it, and you've got your linear parent function that it should reflect over. But hopefully a lot of this vocabulary back up here is making sense, okay? We're gonna pause in this video and pick back up in the next video on what to do when you don't have a graph, when you just have an equation. How do you find the inverse? We'll see you in the next one.